Hello everyone. Today we're gonna discuss and solve simplex method problem. So simplex method is used to solve linear programming problem. And there is many extensions for the simplex method. Today we're gonna solve a maximization problem. So simplex method basically it's inherited the linear algebra solving problem, but it has a different formulation. So back then to linear algebra, when we have a system, for example, with two variables, let's assume we have 2x1 plus 3x2 equals to 6, and we have 1x1 plus 3x2 equals to 5. If we want to solve this problem, so basically we're gonna subtract these two equations using elimination process. Then we will have x1 plus 0x2 equals to 1. Then basically x1 will be equal to 1. We can substitute either of these two equations, so then we will have 2 plus 3x2 equals to 6, which making x2 equals to 4 over 3. But the difference over here in simplex method, we have an objective function, which is basically what is your target, and we have constraint. So basically, when we have any kind of equation, the left hand side always should have the variable. So if you end up with a formulation for a problem like this one, 2 equals 3x1 minus 1. So basically that's cannot be read by simplex or MATLAB linear prog code. So you should have the decision variables in the left hand side and the quantity in the right hand side. So you're gonna reformat this problem, so it's gonna be minus 3x1 equals minus 3. So this is the first concept. Sometimes you might end up with this kind of formula, so 1 over 1x1 is more or equal or less or equal to 2, so you will take the reciprocal of the both sides, so x1 gonna be more or equal to half. And also if you have inequality but your right hand side is in a negative format, so you're gonna multiply both sides with the negative signs, which is with your inequality equation. So let's assume we're having 2x1 plus 3x2 is less or equal minus 2. So basically when you're gonna go to MATLAB or simplex, it cannot read this kind of equation. So you're gonna multiply both sides with minus. It's applicable as when you have a linear algebra system. So this is gonna be minus 2x1 minus 3x2. Then this is gonna be switched to more or equal to 2. So what is the big difference between linear algebra and simplex method? So when we have a linear algebra, we have a system of equation. So let's consider this optimization problem. So basically, assume you are working in a production line, you end up to maximize your profit. So maximize z. So this is your state variable, which is equal to 30 x1 plus 20 x2. And then you have a limited resources are formulated through a constraint. So you have 3x1 plus 2x2 less or equal to 6. So this can be a raw material like bounds you have over here, or for hours for certain machine. Then you have the other constraint. So that might be in bounds for, let's say, another process, call it M2. So these two constraints sometimes are homogeneous. So like for example, this is our labor work, this is our machine labor work. Sometimes they are not homogeneous. So like just only within the equation they should be in the same unit. So like x and the left hand side and the right hand side, so that both coefficients are in same units. But in between equations there is no any constraint. And you consider the economic coordination. So x1 and x2 is more or equal to 0. So this problem cannot be read in in this format. So the program doesn't know what to do with the inequality sign. So basically we're gonna move this inequality and replace a variable, we call it a slack. So this is gonna be switched into slack variable. So this slack variable will present the resources we have here, and this resource will contain the whole labor hours I needed to do it. So this is the slack, like allowance, how much I have in this resource. The other constraint will also allocate the other resource. So this is gonna be plus S2. So here for the allocation for the first resource, second resource will be 0 S1, and this one will be 0 S1. Sorry, this is gonna be S2. So we also have here this one. This is the objective function, and it's still not readable by the simplex method. So he will change this one into the following. So because the same rules applied here, so z gonna be in the also the left hand side with the decision variables. So this is gonna be switched here, and this is gonna be changed to the other side. So this is gonna be minus minus, and we have 0 contribution for the slack variables, because like imagine this. So this is gonna be the labor hours. So this is a kind of cost. It will not contribute anything for your z unless it's start to process it and become a decision variable. So how much we like take from S1 and S2, and we like change them, start manufacturing, then it's gonna be changed to x1 and x2, then it will start up to contribute on z. So the original function. So let's assume we are going to solve this model not using the simplex lure, just like a guess using a linear algebra. So our equation is z minus 30x1 minus 20x2 plus 0 s1 plus 0 s2 equals 0. So why it's 0? Because until now all the resources are still didn't utilize, so we don't have any value for x1 and any value for x2. So x2 and x1 is still non-basic variable. Let's go to the equations. So we have 3x1 plus 2x2 plus s1 equals to 6. Then we have also 4x1 plus x2 plus s2 equals to 4. So someone says, because this equation looked to me very convenient, so like I just only need to multiply it by 10, so I consider to produce like by logic, if you are with a choice to produce between some item can contribute you $30 per item and the other one is 20, so for sure you're gonna produce, if you have only one choice between these two products, so you're gonna choose x1. And when you look to these equations, you will see, yeah, this equation is more convenient. I need just to multiply it by 10 and add it to this one, then switch the resource from here to x1. So then I'm gonna have the contribution for z. So let's see what's happening for z for an instant. So z minus 30x1 minus 20x2 equal to 0. We have multiplying this equation by 10. So we have 30x1 plus 20x2 plus 10s1 equals to 60. So adding these two equations, z plus 10s1 will equal to 60, and we know this becoming right now non-basic. This is our assumption. So we have already contributed for z. Right now we're gonna see how much resource, because we pick up the first equation to be our bottleneck. So let's see how much resource we're gonna consume from the other resource regardless the value for x2. So like our assumption here, x2 is we will not produce anything from x2. We just want to exhaust the both resources to produce from x1. So 4x1 plus x2 plus s2 equals to 4. Then we gonna make this divided by 3. So this equation will be divided by 3. Then multiply it by 4. So this is gonna be 4x1 plus 8 over 3 x2 plus 4 over 3 s1 equals to 8. So subtracting each together, so this is gonna be 0. We know this is a 3 over 3, so minus 5 over 3 by x2 minus 4 over 3 s1. So this is a plus s2 equals to minus 4. So s2 is becoming minus 4. Like I need more resources for, like I need 4 more hours or 4 more units for s2 to go with this plan, which is say I should make x2 equals to 2. Sorry, x1. Still not producing anything from x2, which is not feasible. So this is in not my economic region. So I need a tableau for this thing. I need some rules or governing rules using the simplex method. So then we will rewrite the equations again. So this is z minus 30x1 minus 20x2, which is equal to 0. Then we have 3x1 plus 2x2 plus s1 equals to 6. 4x1 plus x2 plus s2 equals to 4. So let's see how the format for our tableau. So different references using different format. I found this one is the most convenient one, so it's easy, don't need to memorize it. So we have here the variables. We're gonna start with the z. We have x1, we have x2, we have s1, we have s2. Then we have the right hand side. Then we have here the optimality condition. So this will tell me if I reach out my optimal solution or not yet. Here we're gonna readjust the basic solution. So whatever variable we have here, it's only the variable having the solution. Else variable will consider a non-basic solution with the 0 values. So here we just put the coefficient of our equations. So here we just only put the coefficient of my equation. So basically if you have slack and decision variables, so the priority will go for the slack. So this slack will consider having the values. So here s1 from the first constraint and s2 from the second constraint. The coefficient for z for the first constraint is 0, 3 for x1, 2, 1, 0 with 6 right hand side. For the second one, it's gonna be 0, 4, 1, 0, 1. And this is gonna be 4. For the z, this guy will be 1 minus 30 minus 20, 0, 0, and 0. And this is, we call it the bottleneck ratio or the production ratio. So this will decide which is the governing equation, or we will call it the pivot row. Okay. So the same logic applies here. So look to this matrix. This is the identity matrix. So it says S1 equals to 1 and S2 equals to 4. So X1 and X2 equal to 0 right now. So if you have one option to produce between two products, so then always as a maximization problem, only look to the who has the biggest amount with a minus. So as the equation, as the optimality row is less or equal 0, so we didn't reach out our optimality condition. This one is called the pivot column. Or entering variable. So this is meaning I gonna make x1 to be enter my production line. So right now we're gonna look up which variable gonna be my like what is my bottleneck. So this is one which called the pivot column or the entering variable, which is meaning I gonna start producing x1, but right now I'm gonna decide which one of these two variable or these two constraints will limit my production. So what is the bottleneck between these two? So I'm gonna determine it through the ratio theta. So dividing 6 by 3, which give me 2, then 4 by 4, so this is equal to 6 over 3, and this one is 4 by 4, which is equal to 1. So the minimum ratio will decide the bottleneck. So the second constraint is my pivot row or the leaving variable. So x1 will substitute x2. The intersection between the pivot column and the pivot row is called pivot element, which means all the elements or all the coefficients inside my pivot row should be divided by the pivot element. So before starting up filling the second tableau, so we're gonna rewrite the pivot row but divided by its pivot element. So this is gonna be pivot element, which was 4. So this is the pivot row. So my pivot row will be 0z plus 1x1 plus 1 over 4 x2 plus 0 s1 plus 1 over 4 s2, which is equal to 1. I don't need to rewrite the variables, so I just only need the coefficient, so I can rewrite it 0 1 1 over 4 0 1 over 4, which is equal to 1. Then I gonna check out my other rows because I gonna change these rows. So I gonna change this one, then I will also check my optimality condition, but the only way to changing them is through my pivot row. So even if these two equations seems to be more convenient to subtract each other, I couldn't do it though. So this is wrong. So I only gonna change this one. So all the other elements in the pivot column other than the pivot element should be nullified and become 0. So this one should be becoming 0 and this should be becoming 0, but only through my pivot row. So here's my old S1. So then I will put the coefficient, which is R 0, 3, 2, 1, 0, which is equal to 6. Then I'm gonna subtract it by pivot row after multiplying the pivot row by 3. So 0 by 3 is equal to 0, 1 by 3, 3, 3 over 4, 0, again 3 over 4, which is equal to 3. Then I will have my new S1. So this is gonna be 0, 0. So this is my point of interest. I want to nullify it, and make it 0. Then this is 8 over 4 minus 3, which is equals to 5 over 4. 1 minus 3 over 4, which is equal to 3. Then I'm gonna change right now my z formula. So I want to check out this equation. So my z equation would be z minus 30 x1. Sorry, I don't need to write the variables, so I just only to write its coefficient. So this is the old z, which is have 1 minus 30 minus 20, 0, 0, which is equal to 0. And I put here my pivot row. I'm gonna multiply it by 3. So I will put the original pivot row over here, so I'm gonna remember it. So this is 0, this is 1, this is 1 over 4, 0, 1 over 4, which is equal to 1. So 0 by 30 is 0, 30, 30 over 4, 0, 30 over 4, which is equal to 30. Then I add them together. You can multiply by minus, then subtract them. So I have the new z, which is equal to 1, 0. So this is my point of interest, which became 0. Then this one is minus 12 and a half, 0. And this is minus 30. Sorry. So I'm add them together. So this is 30 over 4, and this is gonna be 30. Then I can put them into my tableau. And check out if I reach out my optimality condition. So this is my variables, which have c, we having x1, x2, s1, s2 on the right hand side. Then we have the optimality. So we have here s1 was 0, 0, 5 over 4, 1 minus 3 over 4 with 3, and we have x1 with 0, 1, 1 over 4, 0, 1 over 4 with 1, and lastly we have z, so 1, 0 minus 12.5, and we have 0 and 30 over 5, which is 7.5. It's equal to 30. So we haven't reached our optimality condition yet, because this value is still negative. So I can and this is the only one, so I can do it. So this is my new entering variable. I gonna divide the whole row by 5/4. So my new pivot row, which is returned to x2, so it's gonna be 0, 0, 1, 4/5 minus 3/5 is equal to 2.4. Then I should change the other variables. So this is gonna be I should make it to 0, so I should nullify it, and I'm gonna adjust this one to 0 only through this row again. So here we will put the old x1. We put the original coefficients 0, 1, 1/4, 0, 1/4, which is equal to 1. So this is my point of interest. I want to nullify it, and I put over here the pivot row. So I would like to multiply it by 1/4. So this is 0, 0, 1/4, 1/5. So minus 30, 3/20, which is equal to 0.6. Then I subtract them to each other. So my new x1 gonna be 0, 1, 0, minus 1/5. So this is gonna be 0.4, which is equal to 0.4. Now I want to change z. So I want to change the optimality condition and see if I reach out my optimal solution. So here again I will put my pivot row. So this is gonna be returned to x2, which is 0, 0, 1, 4/5 minus 3/5, which is equal to 2.4. Then put the old z equation. So it has 1, 0, minus 12.5, 0, 7.5, which is equal to 30. Then I put pivot row. To nullify this guy, I will multiply it by 12.5 or minus 12.5, then subtract them to each other. But regardless, the easiest way is just to add them together. So this is gonna be 0, this is again 0, 12.5, this is gonna be 10, this will be minus 7.5, is equal to 30. Then just sum them. So we have here the new z, which is equal to 1, 0, 0, 10, 0, which is equal to 60. So then add these three new constraints to my tableau. So this is my variables, which are z, we have x1, x2, s1, s2, and the right hand side. We have also here my optimality condition, and I having here x2 and x1. So this equation is 0, 1, 4/5, sorry, 0, 1, 4/5 minus 3/5 with 2.4 for x1, 0, 1, 0 minus 1/5, 0.4 and 0.4. For my z equation, we have here 1, 0, 0, 10, 0, 60. So my all coefficient in my optimality condition are more or equal to 0. So zj is more or equal to 0. So I have satisfactory condition. So I have an optimal solution. So let's draw down the summary. So my solution is optimal. I don't have so far not detecting unbounded or invisible solution. I have state variable z, which is equal to 60, and having decision variable x1, which is equal to 0.4, and x2 equals to 2.4. So likely my decision variable are also the basic solution. So my basic solution are x1 and x2. My non-basic solution are s1 and s2. So any variable not was mentioned over here, so we call them non-basic solution. So I don't have any values for my slacks. So what are my binding constraints? Basically they are C1 and C2. So there are any constraint attached with the slack values equal to 0. So what is the non-binding constraint? In this case, the non-binding constraint are my x1 axis and x2 axis. So basically, I don't have any non-binding constraint. There's only the axis, x and y axis. The other thing I would like you to see is for s2 over here, the shadow price was 0, but for s1 it was 10. So then we have here an alternative solution. So I would like you to try it out and give me the alternative solution for this problem, and also try to compare it with the graphical solution. Thank you and see you for the next video.